So here we are once again, chapter 10. Get this moving. Hopefully get you guys back to physics and away from any election nonsense you may or may not be paying attention to because you guys are all young. Okay, so this is rotation stuff and inertia stuff. So it's going to be a combination of the stuff we learned before with a mix of new things. So let's go ahead and get started. There's a lot of summary stuff here at the beginning. If anybody wants the PDFs, like a PDF version of the PowerPoints, just let me know. I kind of stopped posting them in the beginning. It didn't seem like many people wanted them. If you want it, just request it, or I can start posting it again if a bunch of people want it. Okay. So same stuff. Yeah, we'll go through this one by one. So we're getting into a lot of the similar things we did before. So if you guys have been paying attention to the lectures, you've been doing the work and stuff, you're starting to notice that there's kind of a theme. We learn basic principles of something, and once we get past that phase, it's just kind of like copy and paste with slight changes. So things like Newton's second law, we're going to keep using Newton's second law over and over again, right? We're just applying it to different things. The kinematic equations that you learned in chapter 2, going to keep using those, but in different forms, shapes, and sizes. Even the most recent stuff we did, the center of mass stuff, using multiple particles as a single mass, all this stuff comes back. So this is why it's extremely important, as I keep saying every time, that you don't skip anything. You don't miss anything. You don't say, well, this can't be that important later on. All this stuff's used over and over and over, and it doesn't matter if you're engineering or physics or whatever. All this stuff is the very basis of all these majors, so you absolutely need it. So that's basically what this is saying here. We're going to take basically things we learned before and start applying it. So some of the important stuff on here is, again, like I was saying way early on, is you create your own coordinate systems, right? So that means your X and Y axis, you're setting up the coordinate system. Only in this case, we have this reference line here, right? So this is kind of like just setting your X axis, only you're setting the reference line from which you're measuring, say, an angle. So for over here, they've set the reference line in what looks like probably a 45-degree angle. And they're saying this is the reference position, and then we're rotating in a certain direction. The convention is that counterclockwise is positive, and then clockwise is negative. Why is it that way? The word convention basically just means that there was no rhyme or reason to go one way or the other. We all just decided that we needed to pick a single way, and then that's kind of become universal. It's kind of like when you and your significant other are like, what do you want for dinner? And you're like, I don't know, what do you want for dinner? And then you sit there over and over again, and you just kind of pick something, right? Hopefully. But that becomes the convention, right? That's the convention you picked. Like the directions that electrons travel in, if you're doing electricity and magnetism, all that stuff was basically picked by Benjamin Franklin back in the day. From what we know now, it's really annoying because it's backwards from our understanding of it, but that's the convention, right? That's what we picked a long time ago, and we've just stuck with it. So that's basically what this is. Counterclockwise positive. This is positive. Going the other direction, clockwise, because we're used to clockwise. Kind of in your head, you might think it's positive just because clocks and stuff. But whatever, physicists just like to make everything in life difficult. So you have the reference line. This is where you're judging from something's happening. This is the axis of rotation. Standard stuff you're used to here. Here's a radius. Down here, you have the angle theta that we're using. And then we have S. You should be familiar with S from probably like high school math. This isn't arc length. This is just R times theta, right? So S equals R times theta. And we're going to see this more and more again. So we're also going to get into right-hand rule stuff, which I think might be more useful up here. So here is your theta. This is your S equals R theta. So arc length equals R times theta. Again, you're getting in this conversion. Be very careful when you're using degrees and when you're using radians. Whether you're using a calculator or you're just Googling basically calculator stuff, be very careful if it's in degrees or radians. So we're going to start getting into more radians-based stuff here, so you'll have to flip it. So you get used to, when you use degrees a lot with stuff like tangent, sine, cosine, you kind of get used to what the answers are after you use it for so long. So when you start flipping stuff in radians, it becomes like vastly different, right? So you might start seeing answers and you're like, that doesn't look right. But it might just because you're flipping the units in it. And as you flip back and forth, depending on what problems you're doing, it's going to become annoying. Just try to always make sure you're in the right one. Okay, so this isn't new. The degrees and the radians, that should not be new. We've went over that before. This is saying, do not reset theta to 0 after a full rotation. So you should know this already. You have this, you go around one time, right? This is started at 0, now it goes around to pi and then to 2 pi, right? So one full rotation is 2 pi. It's the same as going full in degrees, you go 360, right? So you want to keep adding the degrees so you can tell how many rotations have happened. So just don't zero it out every time because that loses information. And yeah, it has more kinematics of rotation information here. Angular displacements is just the place you start from, subtracted from the place you end up at, or vice versa. Again, this annoying thing where basically they're saying clocks are negative. So your intuitive thing might be to think, again, that a clock direction clockwise is positive. It's not. Just think clocks are negative, clocks are backwards. That'll help you remember negative and positive. It's just saying the same thing again. So here we get, first you have, this is a omega, little omega. And this equals theta divided by t. So this is kind of like what you want to keep in your mind most times. And again, with physics, and it doesn't matter, because I speak a lot in terms of physics and physicists and stuff. I know all you guys are engineers. I don't believe I have any physicists in here. When I post this to the labs, that may be different. I don't know the compositions of the labs because I haven't looked at them. But when we talk about this stuff, remember all this stuff's interchangeable. So if you're giving something in theta, someone gives you an equation at some point, and it has cos theta in it, right? And it has something, the question's asking something to do with time. They're saying, like, this thing happens at such a time, blah, blah, blah. Just remember, like, you have these equations. Like, the 180 equations you're going to carry with you, they should always kind of be in the back of your mind somewhere. You should remember pieces of them. So, like, for instance, theta equals omega times t. So this cos theta can actually equal cos omega t. Right? These are little things. So like when you get something in degrees like this and you're given some kind of time or something like that and you're like, where the heck does time come from? You have to remember little things like this. So you can plug that in and all of a sudden you have a variable of time. So now the cosine is a function of time, whereas it didn't seem like it was when you had just theta in there. So these are just little things to remember. And they're saying that you get the average by, subtracting the change in the initial and the final, same as usual. And then we have here, again, you take the limit as time approaches 0. You get your differential limit. So you get theta, in respect to time, which is the bottom. So basically, theta as it changes in an infinitesimally small amount of time. So that gets rid of basically the average portion, and you're back to just omega, right? So that's your instantaneous. That's how we get it instantaneous. This is an average. It's over some period of time. This is instantaneous. That's what the D represents. So yeah, again, a lot of these are going to say rigid. We only deal with rigid things for the most part. I can't think of any instances you guys are going to deal with non-rigid objects at this point. And the magnitude of the angular velocity, and this is going to get confusing too, because we're going to have like angular velocity, tangential velocity, angular acceleration, tangential acceleration. There's a bunch of these things that are interchangeable, so be very careful when it says something like velocity versus speed versus acceleration. And that's true. That's been true the whole time, but it's going to get more confusing in here. So speed is that's just your magnitude of velocity. You guys learned that in like chapter 2. There's just no direction to it. So let me see. Oh, cat. So we have again, we have our reference line. You have your rotation of axis. You have basically the theta that it started at from the rotation of axis, and well, from the x-axis, and then you have the point that it changed to. So the difference between these thetas here, that's the information we were looking at before. Like, I guess it's listed here. You have your change in theta. So this is the representative of the angular acceleration. This is actually alpha down here. That's an alpha symbol. So this means angular acceleration. So again, we have the change in omega divided by the change in time. And that's going to give us the average. So you can guess probably from the last ones. Go back over here. You can guess from the previous equations that we just looked at that if you take the differential limit of this, we're going to get the instantaneous acceleration, right? And there you go. So you take omega, take the derivative with respect to time, you're going to get the instantaneous angular velocity. And then there's some other things in here like right-hand rule, rotation axes. This is, we'll get to these in a minute. Angular displacements are not vectors. This is a weird thing because angular displacements have both a magnitude and direction. And you say, well, that's the definition of a vector. The problem is they don't follow the mathematical rules of a vector. So you can't do vector addition with angular displacements, which basically disqualifies them from being vectors, even though they have the same properties. So that's just something to keep in mind. They don't have all the same rules. Okay, instantaneous angular speed. So again, I was telling you about this. Remember what this says. This says speed. Remember, it doesn't say velocity. It doesn't say acceleration. Instantaneous angular speed. So again, instantaneous meaning taking the derivative in respect to time of something, whatever it is. In this case, it's speed. So we have the total angular displacement divided by time. Okay. The integral of displacement over time. That doesn't sound very likely. The rate at which angular acceleration is changing, again, that doesn't give us instantaneous. That's more of an average. So that's not working out. The magnitude of the instantaneous angular velocity. And what did we just say? The magnitude of the velocity is the speed. So this is automatically fitting the definition we just went with. A vector directed along the axis of rotation. We haven't even really got to that part yet. So pretty much the one that makes sense is D. It follows exactly what we were just talking about. Okay. If the angular velocity vector of a spinning body points out of the page, and this is where we're going to get into the right-hand rule. So we talked about this a little bit before. Remember the right hand rule is only with the right hand. So be very careful that you don't go like, oh, I'm left-handed, so I'm just going to use my left hand. You can't do that. It is just the right-handed rule. It doesn't matter what your dominant hand is or which one you'd prefer to use. If you use your left hand, you're going to get everything backwards. Again, this is a convention. They know that most people are right-handed, so the convention is to use your right hand. That way everybody's on the same page when you do this. So if you remember, when I explained this to you before, whatever way something is rotating, the direction of rotation, you want to point with your fingers. I'll do it over here. So if it's going around this direction, you point with your fingers until your fingers come together. And now my thumb is facing me. So that's what this is talking about. It's spinning out of the page. So if we did it from, we'll say this is the page, and we curl around this way, which is counterclockwise if you can't see it because it's at a weird angle. So it's spinning counterclockwise. Then my thumb points up. So that is the what they're talking about, the pointing out of the page part. So by giving us that information that the body's pointing out of the page, it must be spinning counterclockwise. Cat here, I don't know why. I haven't seen her in hours. I don't know why she has to pop out right when I start recording. So again, we already said it's counterclockwise. So boom, there's the word counterclockwise. Clockwise, this is out. About an axis that is parallel to the page. That doesn't make a whole lot of sense. About an axis that is changing orientation. Okay. About an axis that is getting longer. And this one doesn't really make any sense either. So you're basically left with B. And again, you don't have to necessarily know what's going on in the problem like usual. If you just do the right hand rule, you know to do that, you automatically get information about the problem that you're looking at. Okay, so this graph shows the angular velocity of a turntable as a function of time. Nobody cares as a turntable or what it is, what the object is. It's saying what is its average angular velocity or angular acceleration now between the time equals 2 seconds to 4 seconds. So we're looking at here is the initial part, and here is the final part. So again, this is just like a kind of get you used to reading graphs again and plots. So remember, this is in omega over here, which is in radians per second, and then you got some time. So if we look at this, we're going to look up here, obviously. So when it goes from 2 to 3, we're at plus 5. And yeah, so whatever. We're looking at acceleration, so these are units acceleration over here. So from plus 2 to plus 3, you have plus 5. When we look at 3 to 4 over here, we can see that this drops over here. If this thing will work, it drops -5 to be at the 0 point, and then it drops another -5. Right, so all you're doing is reading this from 3 to 4. Between 3 and 4, it basically drops -10 points. It goes through the positive portion of the 5s and then into the negative. So if you total it, it's dropping -10. So typical averaging, you just get basically 5 minus 10, I guess. So you get -5, right? And that becomes your average. So again, like very, very minimal knowledge to know what's going on here. You could know absolutely nothing about angular acceleration or what the situation is, what's going on, if you just know how to read the plot. And a lot of people get away with this, especially in higher level physics classes. We get a lot of people that are just math based. They have no idea what's going on. If you shove them out in the real world, they don't understand how things work. They just understand how the math works, so they can kind of cheat and figure out what's going on. That's kind of it's a really useful skill if you can do that. I think it's best to have both skills. You want to be very conceptual, and the math should just be a tool that helps you. The better you are at math, the easier things are going to be. And that just comes with time and practice. So, more learning objectives. And we'll go through all this. So we have basically the equations that we learned in Chapter 2. These are just the standard kinematic equations that we went through. These are very important, if you remember. You're still using them at this point constantly, and you will continue to use them for years. So it's in your best interest to keep these memorized. They have one listed twice. They just simply put a V naught in it, so whatever. It's the same equation. But basically they're saying that, like I was saying earlier, we now have the angular portion of this, right? We have basically the same thing. We've just substituted in the angular portions for the linear portions that were up above. So again, it's nothing super new. It's just a little bit different. So I don't want you to get scared and go, oh no, everything's moving, you know, in circles and rotating and everything's more complicated and I got these weird Greek letters or whatever. It's the same stuff. It's the same stuff. You're just replacing variables. If you just accept that and don't try to freak out about it, it's probably easier. But again, the confidence comes with practice. So the more you do, the better off you'll be. Okay, so here we are back to our arc length. And your classic theta times r. Should have been high school geometry, probably. Okay, and then we have these other portions here. So we have omega. Remember, once again, omega is theta divided by t. So you can actually have v equals theta times r over t. And then what we have up here, we know s is theta times r. So this also equals s over t. If you know this, if you have these equations memorized and you use them often enough that they're in your head, you're not going to be fooled as easily by the physics problems, because they're going to constantly give you stuff and they're just going to throw stuff at you. They're just going to be like, it has an arc length of blah, 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 whatever. And you're like, oh my God, I don't have an equation for that. I'm trying to figure out velocity or whatever. Again, all these things are interchangeable. You can just substitute in other variables to figure something out. So it's a constant game of what variables do you have and what variables do you need, which is like what I was saying way early on in problem solving. So again, here you have t. Capital T is the period. That's the time it takes to go basically one revolution. So you start somewhere, you start some kind of timer, you go all the way around. When it hits back to the starting point, that's one period, which is what this capital T is. If you notice, it equals 2 pi. So we're basically getting our radian conversion piece in there. And then that's times omega. Remember, omega is theta times t. So you get this information there. And you can figure out other things. And you can interchange time and period depending on which you're given, because these two are used a lot together. So this equation may not seem immediately useful, but when you substitute in time, a lot of times the time and period are being used interchangeably. So you may need to use something like what I just wrote over here. Okay, tangential accelerations. We kind of went over this a little bit before. Here is a tangential velocity. So I'm drawing it up here. And you can see it's always perpendicular to the, in this case, the rotation axis and the radius going outward. Like I said, we did some stuff with this before. Basically, they're saying this purple blob here that's kind of outlining, that's the mass you're working with. It's just some kind of unidentified blob. And we're looking at some axis of rotation, and then we're picking a point out in the mass to test or use, or maybe we're rotating it from that point, and then we're looking at the information that's given here. So if we look at this just from the radius perspective and the point out here, then you can get the tangential velocity. So remember, as it moves around the circle, tangential velocity always stays perpendicular. So as you change, this direction constantly changes, which once again, even if it has the same speed, means we have an acceleration because the direction of the velocity is constantly changing. Again, you have your alpha portion here. That's your angular acceleration. And then they are doing the tangential acceleration, which is actually listed down here. So if you take this and multiply it by r, you get rid of the other r components, and then you're left with the tangential acceleration. Same thing down here. This is the a sub r right there and right here. That's your centripetal acceleration. We talked about this a little bit before too in a couple, I think 2 chapters ago, maybe a little bit in the last chapter too. Remember, centripetal is always pointing inwards in the circle, in the center of the rotation. If you use centrifugal, that's the fictitious force that's pointing outward, and we are not getting into that. So don't worry about it. Just stick with this centripetal word. Here it is. Like so. So again, pointing inward. So you got to be very careful with the way things are worded. You could see you have an acceleration here and you have an acceleration here. So if it's just like, what's the acceleration? It depends on which one they're asking for, right? You got to be very careful in the wording. And I saw a problem. This is the problem. This is a problem I've been having with some of the Wiley questions. It's really annoying. I have to go through homeworks, tests, and quizzes that I make, and I have to go through all these problems myself. I have to do them myself, and then I have to check the answers and stuff that's given. A lot of them are wrong, or there's errors, and they encourage me as the professor to email them and say, hey, you got this wrong, or whatever. But I did that in the first couple chapters because there's clearly stuff wrong, and they don't seem too thrilled about it. They're just kind of like, yeah, we're busy. So sadly, they haven't given me a way to fix that stuff on tests and quizzes. So the only thing I can do is find ones that are actually done correctly and give you those. The ones that are done incorrectly, I don't have a way of fixing them, so that causes problems. But getting into this problem as an example, the fan shown has been turned on and is slowing as it rotates clockwise. So it gives you the direction of the arrow of our rotation. It's rotating around this way, clockwise, like a clock. The direction of the acceleration of the point X on the fan tip, so we're looking at a point right here, could be. So again, they're not saying which acceleration it is. Are we looking for centripetal acceleration, or are we looking for tangential acceleration? It doesn't say. So already the problem's kind of flawed. Again, like I said before, if it's centripetal, then we need to look inward. And basically, they're just making a circle out of this thing, so it's rotating this way. So if you just kind of ignore the fan part, it's just a circle that's moving in a clockwise fashion, like so. And this is an exact point we're looking at a single moment in time. Because it's deaccelerating and not accelerating, you're looking at an acceleration in this direction. So you have an acceleration moving inward if it's the centripetal acceleration, then you have the tangential moving outward. So depending on what they're asking for, you have A as the centripetal, and then you have C as the tangential. If we look at this, Lord knows why they have picked D. This is like going this direction. I don't know what they were going for this. No idea. But you can see like what we just did. For instance here, you can't just have a point here, because if you notice, this is the same setup. This is a circle here. We're looking at some point exactly where they're talking about that X point is. So it's basically looking at the same example problem. And then all of a sudden they're going to say that the arrow is going this direction. I don't think so. So yeah, that's just constantly what I have to deal with this stuff. Okay, so now we're getting into kinetic energy. So again, more of the same mixed in with a little new, right? So kinetic energy, we did that before with the spring systems, the pendulums, whatever. We have 1/2 mv squared. You have a couple labs that relate to this. And then again, we're using the summation symbol here, the epsilon, and talking about each point will have a different linear velocity. But every particle will have the same angular velocity. So it's important to keep this in mind because you're looking at systems of particles. Again, a bunch of particles, and this kind of goes back to the center of mass thing, where you have a bunch of particles all over the place or whatever, but if we look at it as one thing and we kind of combine all the masses, you can figure out a reasonable size, shape, and mass for it. Okay, so we're back to velocity, and we're back to omega times r. And then we're looking at this kinetic energy portion again. So you have this kinetic energy, which is now 1/2, as we saw before, 1/2 mv squared, right? So if you look at the v portion, up here, they've simply plugged in the omega r. So now both omega and r are squared. And it becomes important to differentiate those two. So for every radius, all the omegas should be the same. But for every point, as you move around, every radius of every particle, however, you got 10 particles, then this goes R1 through R10, right? Typical summation stuff. This would be like I equals 1 and goes to 10. So if you're familiar with that summation notation that they normally do. These all vary and could be different, and that's why they have to be treated individually. But omega remains the same, so it's pulled outside the parentheses, is basically what they're saying. We call the quantity in parentheses the rotational inertia or moment of inertia, and this is getting into a whole other thing that we're about to talk about. But the rotational inertia that we're talking about here is this mr squared. And if we're talking about a single object, it's mr squared. This is again is using summation, so you can use a bunch of individual things, particles, whatever it is, masses, and add them all together with the summation signs. So yeah, and then more information at the bottom we'll get into. So you have this inertia, you have the summation of it, you have mr squared, rotational inertia. Now saying, let's rewrite it as kinetic energy. So same deal, you have the 1/2 mv squared. So this is just like replacing the pieces the same as I've done before, like the arc length and the theta over t and omega. All these things are kind of interchangeable, so now we can use the things we just learned, the moment of inertia, the I, and then the angular portion omega, and we can insert them into the kinetic energy equation in order to get kinetic energy out of rotating things, right? A good way of putting inertia in general, not just specifically rotational inertia, but inertia in general, it is how difficult it is to change the state of its, the more general term would be like of its movement or its position. So if you take a little rock and you try to move it, it has less inertia than say a giant rock. Harder to move. The same thing as the rock is coming at you, it's rolling down a hill, tiny pebble, small inertia, large boulder, big inertia, right? Mass increases. So they're applying the same kind of concept to rotational stuff. So it depends on speed, axis of rotation. So it gets a little bit more complicated. There's another element in it when you are rotating. And so this is one of the examples that they're giving. They're talking about basically the rod here that's going around this way. So it's just looking, I don't know, can I do this like this and just spinning around this way, right? It's just rotating, like, you can't really see it move it probably, but you can see my fingers move it. So they're talking about that way versus this bottom way, B, here, where it's spinning in this direction, right? So this way is moving the mass farther away from the axis of rotation. This way, all the mass is very close to the axis of rotation, because if you look at the radiuses, you're looking at a radius right here, right? And all the mass is confined in that smaller radius versus the radius here, right? That's a much larger radius. Yeah, so that's kind of just a visual to help you conceptually figure out this stuff in a visual manner. And we'll get into some more stuff here. So continuous body, again, dealing with difficult sizes and shapes of things. The infinitesimal small piece that you're looking at is then dm. So if you get some weird looking mass or whatever, and we want to look at an infinitesimally small piece of this, you just say we'll take a sample, it's a little square or whatever, and blow it up, sort of, because then anything with the D is infinitesimally small, right? It's not measurable realistically. So basically, this is your dm of your mass. You have some total mass, and this is the dm, it's infinitesimally small piece, so that we can figure out the larger sum. This is a weird thing, so it becomes a lot more difficult. Again, something that physicists like to do is put things into common normal shapes, easy algebraic shapes. Things are always, a plane, meaning a 2D square, a cylinder, a sphere, hollow sphere. Simple objects is what they're talking about, common shapes. So here's some of the common ones. So these are derived through the geometry of the shape of the object. So they're all a little bit different. So if you notice before, where is it? When we look at this rotational energy, and they didn't give the object, the inertia that's listed here is mr squared. This is not, you can't just use mr squared for everything. Mr squared is very specific to the shape of an object. And if you're using just inertia in general, because we get into different shaped objects rolling down hills, for instance, then you're going to use these things. So like when a hoop rolls down a hill, you're going to use this mr squared. When a cylinder, meaning the hoop means it has no diameter, it's just whatever, unrealistically thin, right? It has no depth in it. This one does. It's a hollow cylinder, basically. So it's a little more complicated, because now you have two radiuses that you have to add. Now this is a solid cylinder, so it becomes something completely different than the first thing. It's now 1/2 mr squared. So you can see how it changes depending on the object. So the very first thing we did, that initial general equation, was it has to do with this hoop. And the reason they're using this hoop is because we're basically looking at a particle, holding this funny angle, just rotating around some axis, right? So it depends. You have to be careful, and you have to use the appropriate one. For the rotation of stuff, you're generally going to use like this mr squared. These other things are for generalized purpose inertia, moment of inertia objects. Again, think like a sphere rolling down a ramp, a hollow sphere, which is this, rolling down a ramp, that kind of thing. A cylinder versus a larger cylinder versus a hollow cylinder. But in any case, moving on. So this was kind of like similar to the complicated object I drew. And again, we have COM listed here, which is just center of mass. We did that last chapter. You have the rotation of axis, which has been pointed out right here and is directly pointing at it inside here. And then we have some point that we're looking at. Rotation axis through P. So we're looking at this specific point and how that's rotating around that, that axis where basically the center of mass is. So if you use the geometry, you can look at this stuff. Again, this is what I blew up earlier. So you have this dm here. This is this infinitesimally small piece that you've blown up and you made a square. And we're using this for mathematical purposes, right? You have your radius, different geometries going on. They're talking about the axes. The axes must be parallel, and it must go through the center of mass. So you got to pay attention to the parameters of the problem and basically what they're asking for, what they're doing. This is the parallel axis theorem. So this helps us with basically strangely shaped objects like this, not simple shapes, cylinders and spheres and that kind of thing. And like this big M just represents like the total mass, not like a individual particle. Because if this was made of all little particles and it's fluid and moves together or whatever, we need to take a total of all the masses that are involved. And then the h is just the distance between the point of rotation and the point you're looking at, or the point of a specific particle if it's a bunch of particles. This is an example that's in the book. We have this summing of the particles. They go through it in more detail in the book, but basically they're looking at these this situation where you have the center of mass in the middle. So it's right there, and then you have two particles here, particle 1, particle 2. They are the exact same distance apart, which happens to be 1/2 of L, which means this total length here is L, which is listed down here at the bottom also. And the rotation axis is through the center. Right, so that kind of makes it easy. So we can just say, you know, 1/2 ml squared and 1/2 ml squared, and we just get ml squared. And using the parallel axis theorem, now it's rotating through one of the points. So whereas it was going like this, basically, if you have these two objects as particles spinning, now all of a sudden it's pinned at one end and rotating all the way around. So again, when you do this, you got to remember that the 1/2 L portion for this is squared, so you basically get 2/4, and that just becomes 1/2. So this is a half, this is a half, this becomes just a single one or whole. And that's the rest of it's fairly straightforward in the book if you want to look at the example more. Try to go through some of the pieces that you might have been like, where did that come from? Okay. 3 identical balls are tied by light strings to the same rod and rotate around it. So this is confusing because they have this 1m here. So you're like, what is this? Is this mass? Is it mass of the ball, or is this 1 meter away? Considering it says they are 3 identical balls, I'm going to assume that means they have 3 identical masses. So this must be 1 meter away, 2, 3 meters away. Rank the balls according to the rotational inertia least to greatest. So again, if we go back and look at our equations, we can see basically we're going to have some mass times some length. So this is the point of rotation, right? This is basically a rod, and then these things are rotating in whatever direction you want to go with, around, round and around. So when you do this, the length then becomes from the point, the axis of rotation here, over to the center of the particle, like so. If I can stop accidentally writing this pen all over the place. So basically, the longer the length, because we know it's the same mass every time, the greater the inertia. So the least inertia must be 1, and the greatest must be 3. So 1, 2, 3, which is the answer. Okay, so we're going to get into torque. And this will also help you with Lab 10. I believe it's Lab 10 for your 180 classes, and for those who are doing 151. This just has to do with torque. This is going to be way more complicated than the lab. The center of mass stuff is why I said last lecture that has to do with it. This does too. So this is basically, it's much easier in the lab itself because, well, if you had done it, it's just a meter stick. So it's a rigid body that just rotates wherever you set the point of rotation to. If it's just the meter stick by itself, it rotates around the center of the mass in the center. In the lab, you would add masses to each side, making it heavier on one side, so the rotation of axis would no longer be in the center. You have to move it around. They're making this a little bit more complicated because they are, if this is the meter stick, they're not just applying a force. Yikes. I tried to make that a straight line. It didn't work out. They're not just applying a force that is perpendicular to the axis that the rotation's on. So if it's a meter stick like this, it's not just being applied perpendicular completely to it. What they're doing is they're applying a force in some weird direction, right? So this makes it a little bit more difficult. So now we're back to the same things that we've been doing earlier with like inclined planes, boxes on inclined planes, the coefficient of friction, all that stuff. The angle in which the force is being applied is not in an easy place, so we have to break it up into components like we've done time and time again. So you need to figure out the angle, you need to figure out the sine and the cosine, and get the individual components so that you can do it in a linear, one-dimensional fashion. So yeah, that's basically what they're explaining here. You have a moment arm, this line of action, so there's some terms they're using for this. And we'll move on from here. So the torque, so let's look at this. We have R, which is basically some distance, right? It's going to be measured in meters. And then you have a force, right? And of course we're taking the component of it, so it's in the correct direction. But this is basically what we already learned, force times distance, right? Which is work. So we did this earlier. We did a whole chapter on this, right? And it's interesting because if you go through this, the units of torque are a Newton meter. A Newton meter is actually 1 joule. 1 Newton meter is 1 joule. They are interchangeable. If you break down the units of the joule, it is a Newton times a meter, which is kilograms meters per second squared, and then that's the Newton part, and that's times meters. So you get basically, I guess I'll draw a little G there. You get kilograms meters per second squared. So basically you get a velocity squared there, and some mass. So you can have mass times velocity squared. And again, it's good to get good at these units. They're interchangeable. You can figure things out without having all the information all the time. But the interesting thing is that it says, note that 1 joule equals 1 Newton meter, but torques are never expressed in joules. And this is very specific because it works out to be the same units as energy, but we do not want to confuse torque with energy. We don't want to use these things interchangeably. We want to use them in conjunction together sometimes, but we don't want to use them interchangeably, replacing one for the other. So yeah. So again, they're reminding you that torque is, it's positive when it's counterclockwise and negative when it's clockwise. For several torques, you get a net torque, resultant torque, etc. And then they're doing like a little checkpoint here. The figure shows an overhead view of a meter stick. This is the meter stick over here. It can pivot about the dot. So you got a pivot point here. So it's going to rotate in some manner around this dot. So it's basically like right here, and it's rotating around that point, right? So it's not perfectly in the middle where it's rotating like this, and it's not perfectly at the end. It's at some point here. So it's marked at 20 centimeters. All 5 forces on the stick are horizontal and have the same magnitude. Rank the forces according to the magnitude of the torque they produce greatest first. So greatest to smallest. So basically we have to look at all of them. A little confusing. And admittedly, they are kind of trying to trick you to see if you understand this. So again, you have some stick, meter stick, whatever here. So force 1 is right here on this end. So if you apply a force, I'm going to apply it down, you can see you have some rotation, right? So this is moving it. Force 2 is right at the pivot point and is making like this weird kind of angle thing. If you notice, I apply pressure to where it pivots. It's not going to move, right? It's locked into that spot. So force 2 is kind of tricking you because it's being applied right at the pivot point. Nothing's happening. Force 3 is identical to force 1, just on the opposite side, so it moves. Now force 4 is at an angle. So it's still going to move, but it's going to be less than force 3. It's not being applied directly. You're using a component of force 4 to apply it. So the component that's applied in the same direction as F3 is going to be less because you have some portion that is in the horizontal being wasted. And then the final one is F5, which is essentially me pulling this way. So obviously that is not going to rotate it. That doesn't do anything. So you got to be kind of careful where this is. So F1 and F3 are identical, and they are the max. F4 is also moving, but F2 and F5 are both 0, so they're also identical. So you get 1 and 3, as we stated, and then F4 is a little bit off, and then F2 and F5 shouldn't be doing anything to this at all. And if you noticed the lectures as they've gone on, I've gotten away from just showing you the math and the equations and that kind of stuff. We're doing more of these like kind of conceptual questions, because at this point, again, it's the same thing. I shouldn't have to reiterate the same, like this is an equation, this is how you interchange variables in it. Again, it's more the same. You should be getting better at it because I'm just pelting you with the same stuff over and over again. It's repetition. So I think it's more helpful at this point to just go over the conceptual stuff, so that's why we're doing that. A force with a given magnitude is applied to a wheel. So you have a wheel and some center point. The torque can be maximized by sort of like what's going to move this wheel the most or the fastest, depending on how you want to look at it. Applying the force near the axle. The axle is the center parts, so they're kind of referring to like a car wheel. You apply the force near the axle, radially outward from the axle. So they're talking about this direction. So if you have some wheel, again, you apply any, even though this is not a wheel, it's a rod, apply any force to the center, the pivot point, because that's what the axle is. The axle is the pivot point. Doesn't do anything, right? So this isn't going anywhere. Applying the force near the rim. The rim is the outside part. So we already know that if we go to move something like this, the more you extend it, the more torque you get. So anybody that has, I got a weird little clamp here. This would be interesting. I don't think I have anything else. Should have brought some wrenches up. For the probably zero of you that have ever worked on a car, because nobody works on cars these days, except me because I'm old. You get in certain situations where you put a wrench on a nut and you go to move it and you can't do it. It's too tight. One of the tricks you can use is to use a second wrench. This is not a wrench, but this will do. And you can apply it to one end and basically extend the length of the arm that you're pulling on. So this is just a weird little clamp I use to hold things up, backdrops and lights and stuff. So if I apply this on here and then move it, my arm, my lever arm has now increased in length, only slightly, but still. If you use a wrench, it'd be much longer. So if this were a second wrench, and I somehow was able to lock it on there because there's a little loop, it makes it almost twice as long, and then you can really wrench whatever it is over. You get a lot more force applied to whatever it is. So this is a trick I use a lot of times on cars and stuff. I've been having to repair my wife's car, in fact, last week. So it's good to know this stuff, because the more physics you know, the easier life gets. You understand everything much better. So basically what they're saying is you're applying the force out here. So this is already farther away from the point of rotation. So basically you've extended that arm out. So this is good. You want to be somewhere on the rim, because the farther away from the center you are, the more force you're applying. And applying the force near the rim, radially outward from the axle. So again, still applying the force this direction. The position's good because it's farther away. The direction, not good, right? If it has to rotate either this way or this way, applying the force outward that way doesn't help. It's the same thing, once again, as applying it to the center where it doesn't move. That's no good. Applying the force near the axle, we've already talked about this. This is not good. So these are automatically out near the axle. You want to be farther away than that. Applying the force at the rim, tangent to the rim. So now they're saying the same spot. We'll use the same spot, only tangent. So naturally, this is the equivalent of using a rod and applying the force right here, right? So it wants to move, right? So this is an excellent place to be. It's moving in the direction we want to move in. We've used the maximum distance from the center, which is good. The only way to get more force out of this is if you somehow put something, a lever arm on this point, extended it out, and then applied a force out here. This would give you a greater force if you were able to extend that arm. So that was good. Applying the force at the rim at a 45 to the tangent. Now we're talking about going like this way. And again, we talked about this earlier. This is taking components. So you can only take a component of this piece, so it's going to be less than if you directly attached it to it. So you're left with D. Again, Newton's second law never stops coming up, right? So you have the net torque. So the torque that is the total amount of torque that's being applied. It could be applied at several different places, from several different things depending on the situation. You can take the total, and they're saying the torque can now, you can identify this as equaling the inertia times the angular acceleration, right? And if you go back to the equations we did and you look at them, you can break this down and see the different things it works into, and that's helpful. And then again, this is the same stuff we've looked at like 3 different times now. Work in rotational kinetic energy. This is very similar to what we did before. You have the change in kinetic energy over here. So you have a final kinetic energy minus initial kinetic energy, and instead of the 1/2 mv squared, now we have the replacement with the inertia and the angular velocity. So same thing. This is just a replacement of 1/2 mv squared. And then the change in kinetic energy equals the work, because we learned that a couple chapters ago also. And it can be written in an integral form depending on the situation. You got to always do whatever's easiest. If you don't have the situation to do the above, you will have to do an integral, which the point at where you're at right now, you might be like, oh my god, integrals, that's always harder or whatever. You'll get to a point where it's just math. The math is your toolbox, right? The toolbox opens, you pull out a hammer, you pull out a screwdriver. At some point, they're just two different tools used for two different things. You don't go like, oh my god, I have to use the hammer. That's so much more worse than the screwdriver. You're just like, okay, this one's for this thing, this one's for something else. So yeah, constant torque. They just have the difference in the angles. This is just the what they're putting in here, the parameters, the theta final, theta initial. So for, yeah, because they're talking about for a constant, so you put in one variable here, and it's just going to be theta final minus initial. This is basically the answer to the integral. And then power. So power, this is the same thing we did earlier. If you take the derivative in respect to time to work, you can get power. Or you can take the torque and multiply it by the angular velocity. So again, another way that these things are interchangeable. These are good things to have and to hold on to. And then there's a table. These tables of formulas are always pretty good. These things, like, you should already know basically this guy on this side. So this is translational, and then this is rotational. And this book in particular doesn't stress those two terms a lot, the translational versus rotational, but they are two things that will pop up a lot, and you will talk a little bit about it in the lab with the torque lab. Whether, I don't know if anybody's still going to labs, but it's definitely in that lab. So you have your velocity, dx over dt, accelerations, and the derivative of the velocity you just found, and then standard stuff again. So, and then you have the angular equivalence, basically. So if you need kind of like a and oh my god, I'm freaking out with this stuff, you should know all this stuff already. You should have this stuff down pat. Just remember it's interchangeable kind of with the stuff that's on the right. And we're at the summary point. So more just the equations we went over again. So yeah, this will have to do with the lab that you did. Like usual, I have not looked up what the drop dates are. I imagine would be getting pretty close to a drop date, if not already past it. But I'll have to look it up. But you guys should really be paying attention to that. If you're not comfortable with where you're at, if you're not handing the assignments, you're not taking the tests, whatever, you should probably look at dropping. I would advise, if you have never dropped a class, to probably switch it to audit. The only negative side is this is then you get no money back, but I think we're past the point where you would get any money back for the class anyway. So if you switch it to audit, you don't get a W on your transcript. As the professor, when you drop out, it asks me for a grade. And if you are failing at the time, which is usually the reason you withdraw, then you have to get a WF, which means withdrawn at the time failing. Doesn't look good on transcript. So do what's best for you. Look at these things. If you have questions about these things, email me and I'll try to help you out.